Good morning, everybody. I'm Jacopo Papalini, and I'm a first-year PhD student in the University of Parma. And in this video poster, I will talk about supersymmetric localization applied to the JT gravity partition function. So JT gravity is a toy model to study quantum gravitational systems, in particular holography in lower dimensions. And it is characterized by this action where the metric G is coupled to a scalar field, the dilaton, and the action is defined on a two-dimensional manifold. And we also need to introduce a Gibson-Hookean term in order to have a well-defined variational principle. By varying this action, we can find the equations of motion, which I reported there, and we can see that the classical space-time is characterized by a constant negative curvature, and so the classical space-time solution is the so-called IDS2, anti-de Sitter space-time in two dimensions, or also known as the Poincare disk, and the line element can be expressed both in global coordinates, rho and tau, or in Poincare coordinates, z and tau. And in particular, the solution for the equation of motion for the dilaton is phi, which is proportional to 1 over z. So what can be done at this point is try to find the dual theory on the boundary of JT gravity, so applying the Ads-Cft correspondence. And this can be done by evaluating the Gibson-Hookean term on shell, i.e. on the solutions of the equations, so we can explicitly evaluate the extrinsic curvature, and up to a divergent piece that can be removed by holographic renormalization, we find the so-called Schwartian theory, which has a one-dimensional action in terms of a time variable u, and the field is this field F, which belongs to the diffeomorphisms of the S1 circle on the boundary with the normalized length beta, modulo SL2R gauge transformation. So what we find is a one-dimensional quantum mechanical system which is described by the Schwartian theory, and the Schwartian derivative corresponds to the Miltonian of this system. So the aim of my work is to compute the Euclidean partition function of JT gravity exactly through localization. So we have to compute the path integral over the configurations of the metric and of the dilaton, weighted by the JT gravity action plus the Gibson-Hookean term. But this can be better achieved in the first order formulation, where one sees the Wilbein and the spin connection as independent variables, and moreover, one can package these gravitational variables into a single gauge connections, which is spent on the generators of the SL2R gauge algebra. So in particular, gauge transformations acting on this gauge field correspond to diffeomorphisms in the bulk. And so one can replace the gravitational path integral with a path integral over the configurations of this gauge field and an adjoint scalar corresponding to the dilaton, weighted by a BF theory action, which is the equivalent of the JT gravity. Then, for supersymmetric localizations, it turns useful to complexify both the gauge algebra and the fields. So we pass from SL2R to SL2C, and we complexify both A and sigma. So we indicate with capital letters the complexified fields. And then we take another real form of SL2C, which is SU2. And the advantage of this is that SU2 has a positive definite killing form. And then we can compute with this definition the BF action, which is composed by these three terms, and integrating out sigma 1 and sigma 3, just impose the torsion-free conditions for the Wilbein, for the spin connections in terms of the Wilbein. So we recover the second order formulation, and the third term is just the JT action. Once we make some precise prescriptions for these complexified fields, so we can choose a particular contour of integrations in this in the space of complexified fields in order to get the original path integral. However, the BF action is completely topological, and so it cannot be dual to this version, and we can solve this by simply inserting a loop defect, i.e. a potential term of the form trace of sigma squared integrating on a loop, And in particular, trace of sigma squared is a topological operator, and this can be exploited to push the defect infinitely close to the boundary. And then to prove that this is actually equivalent to this version, one can solve the equations of motion for the dilaton, which is covariant derivative of sigma equal to 0. And the gauge connection in this equation is just the pullback of the connection on the boundary on the defect in terms of this reparametrization mode tau prime. And by plugging the solution back in the potential term, one shows that we actually recover the Schwartian theory. So the next step is to deform our space-time disk into an hemisphere via conformal transformation. So we bring the boundary at a finite distance on the equatorial circle, and then we can construct a supersymmetric extension of the BF theory, which has the following action for n equal to 2, vector multiplet P, which contains some gauginos and auxiliary scalars. And the variation of this action under supersymmetry will produce a boundary term on the equatorial circle, and this term has to be annihilated by choosing some suitable boundary conditions, which I reported there. And moreover, we note that this action is actually equivalent to the non-supersymmetric one, and so we are allowed to identify the two path integrals. Now, once we have a supersymmetric action, we can deform the Lagrangian with an exact term, which turns out to be the Super-Yang-Mills action in 2 dimensions, and then the expectation value of the partition function or any BPFs observable will not affected by this deformation, and the bosonic part of this exact term reads like this, from this we can resolve the moduli space, which is given by the one I reported there. But the compatibility with the boundary conditions, in particular the fact that the auxiliary scalar sigma 2 vanishes at the boundary, implies that the field strength F12 is 0, and since the space is simply connected, every flat connections can be gauged to 0, and so the only non-zero moduli space is represented by the constant configurations of the scalar sigma 2. And then the total classical action is given by the supersymmetric extension of the BF plus the defect term on the boundary. But if we evaluate this total action on the locus just determined, well, we are left only with the defect term evaluated on the constant configuration sigma 0. And therefore, the full path integral reduces to a matrix model. So we have to integrate over all possible constant configuration sigma 0, where sigma 0 is valued on the Cartan subalgebra T of SU2. So the only element left is the Z1 loop, which is just the one loop determinant of the fluctuations of the field around the locus. The one loop determinant can be found by expanding every field around the locus to find the quadratic fluctuations of the exact term. And moreover, we can span the gauge field on vector spherical harmonics, the scalar field sigma 2 on the standard spherical harmonics, and the gauginos on spin spherical harmonics. And moreover, each field carries a further index alpha, which labels the root spaces in the algebra. And after gauge fixing, the bosonic part of delta V2 reads like this in a compact matrix form. And so we can read off the bosonic determinant as an infinite product over the harmonics. And we can do a similar computation for the fermionic part, which can be written once again in a compact matrix form. And then collected together both the bosonic and the fermionic contribution, we have a cancellation of terms between numerator and denominator, and we arrive at this final form for the infinite product over the harmonics. And this product can be regularized using the zeta function regularization, and we arrive at the final form of Z1 loop as an hyperbolic sine of pi alpha sigma 0 divided by alpha sigma 0. Finally, collecting all results, we arrive at this form for the partition function as a matrix model. And then we exploit the fact that for SU2, we only have one Cartan generator, which is the third Pauli matrix. And so we can span sigma 0 on gamma 3. And then for SU2, there is only one positive root, which is just 1. And so the partition function is just given by a one-dimensional integral, which is easy to perform, and leads to the result that I have squared in red. And so we succeeded to compute the JT gravity partition function because this result exactly agrees with the previous results already obtained for JT gravity through equivariant localization, sum over representation of the F theory, and conformal bootstrap. Possible future directions of work consist, which I'm going to follow in the future, consist in introducing boundary anchored with some lines and study them through localization, but also higher genus topologies in the bulk or the introduction of defects. So thanks for the attention.